Hello my young friends, I am Naveen Sharma from Toppers Point Shalimar Bagh and I am going to help you in learning chemistry. Our topic of today's discussion is electrochemistry. It is a very important chapter from your examination point of view. It carries 5 marks. So let us start electrochemistry. Now before discussing electrochemistry, I discuss two reactions. You all must have known what are redox reactions. Redox reactions are those reactions in which oxidation and reduction takes place simultaneously. And there are two types of redox. One is your direct redox reaction and another is your indirect redox. Now let us discuss what is direct redox reaction. Direct redox reaction means reduction and oxidation occur simultaneously in a single container. Here we have taken copper sulfate solution and we have dipped a zinc rod in it. Here you can see zinc rod. So this is the setup. Now what are the observations we have seen here? One is zinc rod loses its weight. Zinc rod loses its weight. Second is color of copper sulfate solution fades. Copper sulfate solution, you all must know, it is a intense blue in color, so its color fades. Third observation, very important observation, temperature of the solution. Temperature of the solution increases. That means the solution becomes, hot. Now what could be the possible conclusions for these observations? Now conclusions. First, now the zinc rod loses its weight. This must be due to the zinc solid which is on rod going into the solution Zn2 plus ion aqueous. Here you can see zinc rod loses its weight. So the zinc solid coming into the solution in the form of zinc ion by losing 2 electrons. Okay. Now second is the copper ions aqueous. The copper ions which are present in the solution in aqueous form, they gain 2 electrons which were lost by zinc and convert into copper solid. Here you can see the copper deposited. Now the third observation is solution becomes hot. And why the solution becomes hot? The chemical energy is converted into heat energy. So a direct redox reaction in which the oxidation and reduction takes place in the same container. Now you will ask where the oxidation and reduction occur. You must know, I will tell you. When zinc solid from the rod loses 2 electrons to become Zn2 plus aqueous and the copper aqueous, Cu2 plus aqueous ions, when they gain these 2 electrons, you have seen here, the copper from the solution, I tell you, this Cu2 plus from the solution, they go onto the rod and they gain 2 electrons, okay, and become copper solid. You all must know the loss of electron is called oxidation and the gain of electron is called reduction. So oxidation and reduction are occurring in the same container. Now what is the overall reaction? Now the overall reaction, electrons must be cancelled out from both the sides. 2 electrons, 2 electrons, and we add up these two equations simply. We will get zinc solid plus Cu2 plus aqueous give rise to Zn2 plus aqueous plus Cu solid. So this is the overall reaction. Okay, so this is all about the direct redox reaction. Now let us discuss an indirect redox reaction. Indirect redox, that means reduction, your reduction and oxidation both will occur in different containers. Unlike indirect redox reaction, both oxidation and reduction occurs in the same container. Here the reduction and oxidation will occur in the two separate containers. Now let me show you with the help of an diagram here. So these are the two containers. Okay, and here I have dipped a zinc rod. Okay, in ZnSO4, 1 molar, the concentration is 1 molar ZnSO4 solution. Now we have taken the same rod and the solution having the same cations which the rod is having, zinc and ZnSO4, and here I am taking your copper rod, Cu rod, and with solution copper sulfate solution, 1 molar CuSO4 solution. Now I have connected this with the help of a wire and an ammeter is attached to it. We know the circuit should be complete. Now here the circuit is complete externally, but to complete the circuit internally we have placed another thing here. This is called salt bridge. Now the functions of salt bridge will be discussed later on. Now salt bridge contains the inert electrolytes like KCl, aqueous, or KCl in semi-solid form, or like NaCl, or like NH4OH, etc. Now why they are called inert electrolytes? Inert means they do not interfere with the activities of the ions which are produced in the two separate containers. These two separate containers are called half cells. They are called half cells. So there are two half cells to make a complete cell. Now what happened? Again, zinc from the rod comes into the solution as Zn2 plus ions. So zinc from the rod comes into the Zn2 plus aqueous into the solution by losing 2 electrons. Okay, also some zinc ions are already present in the solution. Like when ZnSO4 will dissociate, it will produce what? It will produce Zn2 plus and SO4 2 minus ions. So equal amount of Zn2 plus and SO4 2 minus ions are already present in the solution. Okay, yes. Now the loss of electron is what? I have already told you the loss of electron is called oxidation. Yes, you are right, oxidation. So here oxidation occur and electrons accumulate on the zinc rod. Now when these electrons accumulate, electrons carry negative charge, so there is repulsion between negative charges. Electron repulsions occur and electrons start moving from here to here. And the movement of electron constitutes what? Movement of electron constitutes electric current. This is what we have to study in this electrochemistry. We are producing electric current with the help of the energy of a spontaneous redox reaction. Now what are spontaneous? Spontaneous means which go on their own. So we are producing electric current with the help of a energy of spontaneous redox reaction. So if electrons are moving in this direction from zinc rod to the copper rod, current will move in the opposite direction. We know the sign convention of current. Okay. So it is moving here. Deflection is always seen in ammeter when this current is produced. You already know. Okay. Now when these electron reaches the copper rod, the copper ions are already present in this solution. Cu2 plus equal amount of SO4 2 minus is also there. SO4 2 minus, SO4 2 minus and Cu2 plus. When these Cu2 plus ions in solution, in solution we always write aqueous, and ions on the rod we always write solid. So Cu2 plus aqueous ions, these ions gain 2 electrons. From where they gain 2 electrons? The electrons which are coming from this zinc rod. Okay, so they gain 2 electrons and deposit at copper rod, Cu solid. And we already know the gain of electron is called reduction. So here reduction occur. Now I will ask you, what is the overall reaction? You simply say the 2 electrons from the opposite side cancel out each other, and we will get this zinc solid plus Cu2 plus aqueous give rise to zinc 2 plus aqueous plus copper solid. So this is the overall reaction. Okay, now Zn2 plus ions are already present in the solution, because when this your ZnSO4 dissociate, it produces Zn2 plus aqueous plus SO4 2 minus aqueous ions. Also Zn2 plus are entering into the solution from the zinc rod. So the population of zinc ions increases in the solution. The excess of positive charge, slowly the excess of positive charge accumulate in the solution. Now what this positive charge do? This positive charge holds these electrons. It do not allow these electrons to move. So current stops. Now what happen when your TV remote do not work? What you do? Yes, tell me. Yes, what you do? You just tap that remote and then the channel, then you press the buttons, then it works. Similarly we can explain here the phenomenon, how this phenomenon occur. Now what I told you the positive charge accumulate in the solution which holds this electrons and do not allow the electrons to move, thus the current stops. Now here comes the role of your salt bridge. Now what does salt bridge do? Salt bridge already present ions, inert electrolytes like Cl plus K, Cl minus K plus, Cl minus K plus, K plus, Cl minus K plus, K plus, Cl minus. Already the K plus and Cl minus ions are already present in this your salt bridge. Now what happens? When this positive charge concentration increases in the solution, this positive charge attract these negative electrons into the solution. So what happens? When this negative charge falls into the solution, it neutralizes. It do what? It neutralizes the excess of positive charge which was created when zinc ion population was become high in the solution. So What does salt bridge do? Salt bridge will neutralize this chloride ions from salt bridge will neutralize the excess of positive charge. Now the positive charge reduces, electrons again start moving. Just like your remote, no? When you tap your remote and the channels start changing when you press the button, similar manner. Now what happens at the copper rod? Now at the copper rod you can see the Cu2 plus ions are converted into your Cu solid on the rod. That means the positive charge reduces, but the sulfate, due to the presence of sulfate ions, the negative charge in this half cell increases. Now again this negative charge attracts the positive charge from the salt bridge, and the positive charge will neutralize. Okay, are you getting? This positive charge will neutralize the excess of negative charge. So what are the functions of salt bridge? So the functions of salt bridge, we can write the functions of salt bridge. First is, I already explained this to you. What? Yes, it maintains. What it maintains? It maintains the electrical neutrality. It maintains the electrical neutrality of the circuit. It maintains the electrical neutrality of the circuit. Second is, it complete, you already know now, for electric current to flow there must be a complete circuit, a closed path of electric current. So it completes the circuit internally. So these are the two important functions of salt bridge I have told you, and I have explained you the direct redox, in which the oxidation and reduction occurs in the same container, where the chemical energy was converted into the heat energy. Now what we have done in the indirect redox reaction, we have taken two separate containers in which oxidation and reduction occurs separately. Now I must tell you, the rod on which oxidation occur, you know na, zinc is losing 2 electrons. So the rod on which oxidation occur is called anode, and it is also called negatively charged electrode because electrons are accumulated here. Okay, and this this copper rod where reduction occur is called cathode. You all people must be having confusion in this, ki anode is negative or anode is positive, or what is the sign for cathode, positive or negative. The simple rule is, you always see oxidation reaction and reduction reaction, the electrode on which oxidation occur. I am telling you, the electrode on which oxidation occur is your anode. Always in any kind of cell, whether it is electrochemical cell, we are discussing here electrochemical cell, galvanic cell, Daniell cell, or electrolytic cell, the electrode on which oxidation occur is always called anode, and the electrode on which reduction occur is called cathode. Now I am telling you one rule that is called lone. Now what is lone? Easy way to remember this, na? This is left, L is left, oxidation, anode, negative. Okay, so the electrode on which oxidation occur is your anode, and it is always present in the left hand side, and it is negatively charged. Okay, so you can remember like this, low from lone. Okay, so the overall reaction, this is your overall reaction in which oxidation and reduction occur simultaneously. I have told you the functions of salt bridge and the electrochemical cell, how does it work. Now next topic is cell representation. It may be asked in your exam, cell representation. Now for cell representation also I have created a, you can say, a rule, As such, it is not a rule, but I have created for easy remembrance. ABC rule. Now what is ABC rule is? This is anode and B represent bridge, yes, and C represents cathode. So ABC. Like if I have to represent this cell, zinc copper cell, on cellular representation, how I will represent it? Anode. Now what had happened at anode? Anode zinc solid was converted into zinc 2 plus aqueous ions. This was happened at anode. And then the bridge. Bridge is with two parallel lines. We draw a bridge. And then copper 2 plus aqueous is converted into copper solid. This was happened at cathode. Okay, so this is the cell representation of your zinc and copper cell, which I have explained already. So you already know what are redox reaction. The oxidation and reduction occur simultaneously. I have told you the direct redox. In direct redox, the chemical energy was converted into heat energy because there is no path for the electrons to move. Because if once electron move, they constitute electric current. For that matter, I have done indirect redox, in which I have what? Place the two rods in the different containers and a path is given to electrons to move, to produce electric current. Are you getting my point? Why I have told you about the direct redox and the indirect redox. This is how we can produce electric current with the help of cell. So your galvanic cell, your Daniell cell, your voltaic cell, they all work like this only. Okay. So now the cell representation, I am coming back to the topic. The cell representation, I have represented the cell. Now I am giving you the question example. Actually you have to represent the copper AgNO3 cell. Yes, this cell you have to represent. Now what is written at in the left? Copper. So copper is your anode, work as anode, and your silver will work as your cathode. Now if I write the cellular representation, you already know the copper, if it is at anode or work as anode, it will lose electrons. Okay, so copper will if I write the equations for you first, like copper solid will go into the solution to become copper 2 plus aqueous plus 2 electrons. Okay, and yours what silver will do? Silver Ag plus. Are you getting? This Ag plus will gain one electron. Only single electron is required to neutralize this single positive charge. Okay, so this will become this your right here aqueous, Ag solid. So these are the two half reactions. Okay, now this Cu2 plus Cu solid give rise to Cu2 plus 2 electrons. Now Ag plus aqueous, this is aqueous, plus electron give rise to Ag solid. Now what I have told you? I have told you your electrons must be cancelled out from both the sides. So we will multiply the equation by 2 and this will become 2Ag, 2 electron, 2Ag. These 2 electrons will cancel out. Now what will be the final equation? The final equation is Cu solid plus 2Ag plus aqueous, yes, and Cu2 plus aqueous plus 2Ag solid. Now what is the cell representation? The cell representation for this is Cu solid becomes Cu2 plus aqueous salt bridge. You know what is ABC? Yes. So Cu solid becomes Cu2 plus aqueous, and then Ag plus aqueous become what? Become Ag solid. So this is the cell representation for this. Let me give you another example to make you more clear. So we have here nickel solid to another different type of example. Actually, nickel solid to nickel 2 plus aqueous bridge, and your Ag plus aqueous becomes Ag solid. Now what the question is, or what the example is asking here, write the two half cell reactions and the overall reaction. Now what this is asking, write the two half cell reactions and the overall reaction. Now you can easily write the two half reaction. What is anode here? You know this is A, you know this is B, you know this is C. So this is ABC. So anode is what? Nickel, and nickel is becoming what? Nickel 2 plus aqueous, and we already know nickel solid will change into nickel 2 plus aqueous by the release of 2 electrons. Okay, and this Ag plus aqueous will gain a single electron to neutralize a single positive charge to become Ag solid. Now again we have to multiply the equation, this second equation, by 2. You know why? Because we have to cancel out these 2 electrons from the main overall reaction. Okay, so this will become like 2 electrons and 2 electrons cancel out each other. The nickel solid plus 2 Ag plus aqueous will give rise to, yes, nickel 2 plus aqueous plus 2 Ag solid. Very good. Yes, I hope you must be clear with the cell representation, how we write cell representation. It is important to know the half cell reactions and the overall reactions, because sometimes for writing the cell representation you must know how many electrons are taking part here. Okay, so now we are moving on to the another topic, or you want me to revise this? Okay, now I will give you a summary question that will clear your all revise your actually all the concept which I have already told you just now. I will give you. Yes, I'm moving to the another topic here. Now the next is your electrode potential. Next is your electrode potential. Now what is electrode potential? You already know current can pass when there is potential difference, between the two electrodes only the current can pass. Okay, now there is a tendency of an electrode. It is a tendency of an electrode to lose or to gain electrons when kept in the solution of its own ions. Okay, so it is a tendency of an electrode. We cannot make any electrode to lose electron or to gain electron. It depends on the electrode only. Like I discussed this, like if I have placed this, again I am taking the same example which I have taken. If I take this zinc rod and the solution is ZnSO4. So some zinc ions are already present in the solution, you know, I have explained you. Yes, including sulfate ions also. Okay, so what could be the possibilities of the reactions to occur? One is your this zinc 2 plus aqueous ions which are present in the solution will gain the 2 electrons, and or they hit the rod, actually they hit the rod and gain 2 electrons from the rod. Another is your zinc solid which is present on the rod will lose 2 electrons to become or to come into the solution with these 2 electrons. Both the possibilities can happen. This is the tendency of an electrode. But what we have seen, what is generally seen in zinc case, there is no change. Zinc do not behave like this. It always, when the electrode, I am telling you, what is electrode potential? It is a tendency of an electrode. We cannot do anything in that. It is a tendency of an electrode to lose or gain electrons when it is dipped into the ions of its own solution. Okay, so what zinc do? Zinc, when dipped into the ZnSO4 solution, it will always lose 2 electrons. It will become Zn2 plus aqueous plus 2 electron. It always lose 2 electron. So this is what? This is oxidation potential. This is what? This is oxidation potential. Similarly, the rod can have reduction potentials. Okay. Now, when zinc come into the solution, it will lose 2 electrons, and the electrons get accumulated here only. So the excess of positive charge is created in the solution, and the negative charge is created on the rod. So due to the difference, you can see here, due to the difference in the charge or the charges between the rod, yes, and the solution, a potential is developed. A potential is developed, or a potential difference is developed. I will say it. Potential difference is developed. Now I will give you the definitions of oxidation potential and reduction potentials. Oxidation potential. Okay, students, oxidation potential. Now, what is oxidation potential? Again, it is the tendency. I have already told you. So, it is the tendency of electrode to lose electron. When it is oxidation, electrode will always lose electron. So, tendency to lose electron or to get oxidized when it is placed in the solution of its own ions. Okay, so a general oxidation reaction, like M is your metal and will convert into Mn plus. I don't know what the charge is, so I have put it like N plus how many electron then? If the charge is N plus, N electrons. Yes. Now what is the reduction potential? So reduction potential here. Okay, so again it is a tendency. What it is? It is a tendency of the electrode. It is the pure tendency of the electrode to gain here. If the reduction is there, gain electron. To gain electron or to get reduced. When dissolve in the ions of its own solution. Okay, so I have explained you what is the oxidation potential and what the reduction potential means. A general reduction reaction is like Mn plus aqueous metal gains N electron to become M solid. So what we have discussed so far, we have discussed what is direct redox reactions. We are discussing the redox reaction earlier. So direct redox reaction in which oxidation and reduction occurs simultaneously. Okay, and we have they are seen the container becomes hot due to the chemical energy conversion into the heat energy. Then we have seen the indirect redox reaction. In indirect redox reaction, you have seen we have taken two half cells. One is your zinc rod in which zinc rod is dipped, and another is your in which copper rod is dipped. Okay, and what was the working I have already told you. I have explained you with the help of this simple and easy diagram. Let me show you. Where it is? Okay, yes. I have already explained this, and I have told you the concept of lone. Then I have told you what the cell representation is. Wait. Okay. What the cell representation is, I have told you by this ABC rule. This is, you know na, what is A? Yes, anode. B, bridge. C is cathode. I have told you this. Then how to write the half cell reactions. Okay. And functions of salt bridge we have discussed, and now we are then I have told you the electrode potentials. Okay, so electrode potential, the tendency of an electrode to lose or gain electron when dipped into the solution of its own ions. Okay, okay, I have told you this. Then oxidation potential and the reduction potential I have made you clear with this also. Now I'm moving to the another subtopic in this. This is standard. Yes, standard electrode potential. Now the standard electrode potential, we denote it by the symbol E naught. Wherever we talk about standard, like in class 11th we have studied this, your standard things, standard energy, standard enthalpy, we always mark with this naught. Yes, okay. In thermodynamics we have done this, na? Okay. Now what is standard electrode potential? Now first, the electrode potential, I'm telling you, the electrode potential which is measured at standard conditions. Now what are the standard conditions? Actually the standard conditions are when the concentration of the solution, that is ZnSO4 solution or copper sulfate solution, is 1 molar, temperature is 298 Kelvin, and if the gases are involved, pressure is 1 bar. These are the standard conditions. Okay, the electrode potential measured at these conditions is known as what? Standard electrode potential. Now the thing is, how we can calculate, how we can measure the standard electrode potential. You know that your oxidation and reduction occur simultaneously. They cannot be occur individually. Okay, so if we want to calculate like electrode potential of zinc, or the reduction potential of zinc or the copper for that matter, we cannot calculate them individually. Why? There are two reasons why we cannot calculate them individually. One is your redox, I'm telling you, redox occur simultaneously. Means if one species is oxidized, then another has to be reduced. They occur simultaneously. Like in direct redox you have seen, I have taken zinc rod in copper sulfate solution. One zinc is oxidizing and copper is reducing. Okay. And the second one, why we cannot measure the individually we cannot measure. Why? Second is oxidation potential and the reduction potentials are the relative tendencies. Are what? Are the relative tendencies. Yes. Now what do you mean by the relative tendencies? Like if I place this zinc rod with this copper rod, so what we have seen, seen this zinc behave as anode. I have already discussed this, yes, and the copper rod behave as cathode. If I set up another cell in which a copper rod is set up with this suppose your silver rod, now here the copper rod will work as what? Your copper rod will work as anode. Yes, this is observed. Experimentally this is observed, and your silver rod will work as what? Cathode. So they are the relative tendencies. One rod at the same time can behave as cathode or as anode. Okay, so they are the relative tendencies. So when we have to calculate the reduction potential, we will calculate these relatively with some other metal. Now if suppose if I say student got 95 in your mathematics, okay, 95 marks in maths, and at the same time the another student got 98 marks or 98% in 98% in your chemistry, say. Okay, so which student is better, 95 marks in maths or the student with the 98 marks in chemistry? You will say, how can we compare? The subjects are different. We cannot compare the both. We can compare the both if the marks of both the students in mathematics are known or marks of both the students in chemistry are known. then only we can compare, na? Similarly, to compare which is the better oxidizing or which is the better reducing agent, we have made a standard electrode. Now we are doing, we are just have to calculate the what reduction potentials, na? And reduction potential, what is the reduction potential of zinc, what is the reduction potential for copper, what is the reduction potential for magnesium, say for iron, say for silver. We cannot make different pairs every time, because it will not give the comparison, right? Okay, so what we have done, we have taken a single rod that is called She. Now what is She? She is standard hydrogen. What is she? She is standard hydrogen electrode. Now if I have to calculate the electrode potential for zinc, I will connect zinc rod in the one container, and another container I will take this standard hydrogen electrode. If I have to calculate this reduction potential for copper, I will connect copper in the one container and She in the another. Similarly for iron, magnesium, we will take She as the reference electrode. So it is what? It is the reference electrode. Okay. Now what is the construction? First I will tell you what is the construction of this standard hydrogen electrode. Here 1 molar standard, 1 molar HCl is taken, okay, and an inverted test tube. This is platinum wire coated with your carbon black, right? Okay, and H2 gas is passed, and what will be the pressure of this gas? The conditions are standard 1 bar. Yes, you already know this. Okay, and the temperature is maintained to what? 298 Kelvin. So this is the construction of your standard hydrogen electrode. This, look at the diagram. This is what? Platinum wire coated with carbon black, and this is the wire. Okay. Okay. Now how we can represent this? We represent the hydrogen electrode like PT, H2 gas, 2H plus ions, or 1 molar we can write. Okay, so this is how we represent the hydrogen, standard hydrogen electrode. Okay, now this standard hydrogen electrode can work, this electrode, this can work both as anode as well as cathode. So this hydrogen She can work both as cathode as well as anode. It depends on the metal with which you are connecting this. So it can work both as anode as well as cathode. Therefore it is also called reversible electrode. Therefore it is also called reversible electrode. Now by convention we have taken the electrode potential of hydrogen, standard hydrogen electrode, potential of standard hydrogen electrode as 0 volt. Actually the potential is 0.0012, and we have approximately taken it as a 0 volt. Very less potential hydrogen electrode is having, so it is 0 volt. That means She do not have any tendency of its own, to undergo oxidation or reduction. That is why the potential is 0 volt. It will do not undergo oxidation or reduction at the on its own. Okay. When the reduction occur, how and when the oxidation occur, how we can represent this your She. Now when the reduction oxidation occur, first we will discuss this. Now oxidation occur. Now what is oxidation? The loss of electrons is called oxidation. So H2 gas converted into 2H plus aqueous plus 2 electrons. So this is the half cell reaction for oxidation when She behave as your anode, because you know what is lone? Yes, yes, oxidation means anode. Yeah. Now what is the reduction then? Now what is the reduction half cell reaction? The reduction half cell reaction for She is 2H plus aqueous plus 2 electrons will give rise to H2 gas. Okay, am I clear with you? Yes. So I have discussed why there is a need of a reference electrode She. Yes. Okay. Okay. Now we will move on to the calculation part. Okay. So the measurement. Yes. Yes. Measurement of standard electrode potentials. Now how we can measure these standard reduction potentials with the help of She standard hydrogen electrode. Now, again I am taking this example here, the two half cells I am drawing. Yes, in one I have taken this zinc rod, in another I have taken what? Yes, She reference electrode, and I have connected this time the two half cells with a voltmeter. Okay, this is why to calculate the voltage or the EMF of the cell. Now what I have taken here, 1 molar ZnSO4, conditions are standard, temperature is maintained 298 Kelvin, and here is 1 molar HCl solution, temperature. Okay, now yes, very important, salt bridge. Yes, you cannot forget, salt bridge is there. Now when the setup is ready, the current start flowing. The voltage in this voltmeter I have placed here, it comes out to be 0.76 volt. Okay, now experimentally we have a relation, that is E naught cell, that is the cell potential, or we can say standard cell potential is equal to what? Is equal to E naught cathode, yes, minus E naught anode. So this is the general formula we have. We already have this formula. Okay, so okay, now what is the cell potential here? Cell potential is coming out to be 0.76 volt. Yes, 0.76 volt. Now what is cathode here? What is cathode? Now how will you, now some people ask me how you can attach this zinc rod as anode only and this She as cathode. Now I have just set up the cell and I have seen what happened. Actually what happened here, automatic, it is a tendency of electrode. I cannot do anything in that. So what happened? This zinc solid start moving into the solution. This is seen actually in the setup. Okay, so that is why I have considered this as anode and I have considered She as cathode. Okay, this I have seen in the setup only. So the cell potential is 0.76 volt and your cathode potential, what is cathode here? She. Yes. And what is the potential of standard hydrogen electrode? Yes, it is 0 volt, 0 minus E naught anode. E naught is unknown to us. Okay, so it comes out to be minus E naught anode is equal to 0.76 volt, and this E naught anode value comes out to be minus 0.76 volt. So this is how we calculated the standard electrode potential for zinc. Now I will give you another example to make you clear. Like similarly, we can calculate the standard electrode potential for copper. Here is given Cu E naught, Cu2 plus 2, Cu we have to calculate. This is what? This is the reduction potential. Okay, reduction potential. Now why we are calculating only reduction potentials? Here also, here also, although at anode oxidation occur, but when I write this 0.76, this zinc 2 plus 2 Zn value is minus 0.76. Yes. So this is what I am writing here, what? 76. I am writing here what? I am writing the reduction potential. Why oxidation occur at this zinc, but I am writing reduction potential. Why I am writing reduction potential, I will tell you later. Okay. Now if I have to calculate the reduction potential for copper, now how can we calculate this? You already given the voltmeter reading in the cell is 0.34 volt, and you know the formula, and the cell representation is also given here, like H2 gas to 2H plus aqueous bridge, then your Cu2 plus aqueous to form Cu solid. So what is cathode here? You already know by the rule ABC, I have discussed with you. So this is cathode, this is bridge, this is the anode. Okay, so E naught cell is equal to E naught cathode. This relationship we have, E naught anode. Okay, so E naught cell your 0.34 volt, E naught cathode, I can write this copper rod, and the anode is here She, and what is the standard electrode potential for She is 0. So what is the reduction potential for copper is 0.34 volt. Yes, 0.34 volt. Okay, so we are always calculating the reduction potential. I will tell you later. I have told you whether it is oxidation, whether it is reduction. Like earlier I have given you this E naught Zn2 plus 2 Zn is minus 0.76 volt. If I write E naught Zn2 plus, now this is the reduction potential. Okay, and what is the oxidation potential here? Oxidation potential, if I convert this reduction potential to oxidation potential, it will give, the sign will change, minus 0.76 volt will become 0.76 volt. Okay, now I will tell you later on why we are doing this all reduction potential, why we are not considering any oxidation potential here. Okay, so I have told you how to calculate or how we can get these values for zinc and copper. You don't have to worry for these value to remember, they will be given into your exam. Okay, now next is your electrochemical. Next is your electrochemical series. Next is your electrochemical series. Now what is electrochemical series? In electrochemical series, the standard electrode potential, if I am writing here E naught, okay, it is understood. This is what electrode potential I am talking about. The standard electrode potentials are measured with what? With She, and then these are arranged in increasing or decreasing order. This series, increasing or decreasing order of their reducing strength, then this series is called electrochemical series. Now one thing, if I write like E naught Zn 2 plus 2 Zn is 0.76 volt. and E naught Cu2 plus to Cu is 0.34 volt. Can we compare? What is this? This is what? This is the oxidation potential. Yes, you can see Zn2 plus is converting into Zn. So this is what? Oxidation potential. And here copper, we can see what? Cu2 plus is converted into Cu. So this is what? This is reduction potential. Can we compare? Now again the case arises, marks attained by a student in mathematics 95, marks attained by a student in chemistry 98. We cannot compare. Subjects are different. That is why we cannot compare this. Which one is better reducing agent, which one is better oxidizing agent? We cannot compare. So in order to compare, we always take reduction potentials. Like for zinc, reduction potential is minus 0.76 volt. For zinc, reduction potential is minus 0.76 volt. For copper, the reduction potential is 0.34 volt. Now we can compare because both are in reduction potential. Now we will do the applications of electrochemical series, and in that I will tell you how you can find out which one is the better reducing agent, which one is the better oxidizing agent, and other important applications we will discuss. Okay, now the applications, now is what? Now is the applications of electrochemical series. Okay, now what are the applications? First application is to predict what? To predict the relative reducing or oxidizing nature. How we can predict? Now the electrode having more negative standard reduction potential, more negative, okay, better is the reducing agent. Better is the reducing agent. Okay, and similarly we can say the electrode having more positive standard reduction potential, okay, will be better is the, yes, better is the oxidizing agent. Yes. So you know, like if I give you example, magnesium, zinc and iron are having their reduction potentials like Mg2, this is reduction, Mg2, E naught Mg2 plus 2 Mg is minus 2 point, let me give you the values. The value is minus 2.36 volt. For E naught Zn, you already know, Zn 2 plus 2 Zn is minus 0.76 volt, and for your this iron is Fe2 plus 2 Fe, it is given your minus 0.44 volt. Now the question is arrange them in the order of increasing, reducing strength. Okay, so what I have given you example. The electrode potentials of magnesium, zinc and iron are given to you, and you have to arrange them in the order of increasing, reducing strength. Okay, now what I have told you, the electrode whose electrode potential is more negative is the better reducing agent. So here you can find zinc is having the least negative. Zinc is having the least negative. So zinc is the least strength of reducing agent. Okay, so zinc is having the least negative, then is your iron, and then is your zinc, oh sorry, magnesium, so this is the increasing nature of reducing nature. Okay, now we move on to the second application. The second application is to calculate, this is to calculate what? To calculate the EMF of cell. Now what is EMF? EMF is the electromotive force. It is nothing, that is E naught cell only. Okay, now how we can calculate the E naught cell? I have discussed this with you already. You know, E naught cell is equal to E naught cathode minus E naught anode. Okay, now here I am discussing the same example which I have already discussed with you. Zinc solid becomes zinc 2 plus aqueous bridge Cu2 plus aqueous Cu solid, and the reduction potentials of this zinc and copper are given to you. For zinc it is minus 0.76 volt, for copper it is 0.34 volt. Now you can easily calculate, you can calculate E naught cell, that is E naught, what is cathode here? Copper is the cathode, no? Cu2 plus Cu minus E naught Zn2 plus Zn. So your copper is 0.34 volt, your zinc is negative 0.76 volt, and this answer comes out to be 1.1 volt. So this is how you can calculate the EMF of cell when the reduction potentials are given to you. From this we have we known that this is anode and this is cathode. ABC rule. Okay. One more thing I want to discuss with you. Actually, the more negative is the electrode, okay, it will become anode only. Okay, it will become anode only. The more negative, it will become anode. And at anode, what happen? At anode, oxidation occur, and the species which get oxidized is the reducing agent. You all must know. Anode, what? Anode, oxidation occur, and the species is the reducing agent. Now what I want to discuss with you now, you all must remember the reactivity series we have done in our class. From class our 7th we are doing this reactivity series. Now what is the reactivity series? If anybody can answer, yes. Okay, now I will tell you a thing to remember this reactivity series. What is Kedar Nath ka Mali? Now this is how you can remember. Kedar Nath ka Mali आलू ज़रा फीके पकाता है. Okay, so this is how you can remember this reactivity series. Potassium, sodium, calcium, magnesium, aluminium, zinc, iron, lead and hydrogen. केदारनाथ का माली आलू ज़रा फीके पकाता है, and after that you get Cu, Ag, Au and Pt. Now the element which is at the top of the reactivity series will be having the most negative, electrode potential. You can always see, like we have discussed this, what in the whole class we are discussing this zinc and this copper only. We have discussing these two examples frequently. Zinc is at the top in the series, we can see, and copper is below. So which is having the negative reduction potential? Here you can see zinc is having negative reduction potential, copper is having positive reduction potential 0.34 volt. Anything below hydrogen will have positive reduction potential. Okay, like I have discussed this example with you, magnesium, iron. So iron was having negative 0.44 volt Huh? Again iron comes below this zinc. Okay. Okay, you can change here na. This iron will be the least. Okay, I have done this here, Mg. You can change, yeah. Okay. Now I hope you must understood what the reduction and oxidation potentials and how with the values of these reduction and oxidation potential we can find the better reducing agent or the better oxidizing agent here. Huh? Okay. So next is your third application, to predict what? To predict the spontaneity, to predict the spontaneity of a redox reaction. Huh? Now how we can predict the spontaneity of a redox reaction? For example, I am giving you this cell na? Ag plus aqueous bridge copper aqueous copper solid. So we know, this is known to us, if E0 cell is positive, reaction occurs spontaneously on their own. Reaction occur spontaneously, or the cell will work. Okay. And if the E0 cell is negative, are you getting my point? If the E0 cell is negative, the reaction will not occur spontaneously. The reaction will not occur spontaneously. It doesn't mean that reaction cannot occur in any case. Reaction can occur in backward direction but cannot occur the direction in which you have taken. Or the cell will not work. Cell will not work. For example, the cell I have given you in the example, the E0 values for your Ag plus 2 Ag, the reduction potential for silver is given to you, that is 0.80 volt. Reduction potential for copper, Cu2 plus copper, is 0.34 volt. You already know how to calculate the EMF or the E0 cell. Formula: E0 cell equal to E0 cathode minus E0 anode. Now what is cathode here? In the cell representation you can easily tell me. Yes, tell me what is the cathode here? Copper. Yes, ABC rule, you already know ABC rule na. So copper is your cathode here, okay, and silver is your anode. So what is the formula? Cathode minus anode. So 0.34 minus 0.080 will give you the value negative of 0.46 volt. So what the E0 cell value is? It is comes out to be what? Negative. That means cell will work or not? No, the cell will not work. Am I clear with this? Yes. Okay. Next. So next application is, you can say this is the fourth application, whether the cell, whether the element will evolve H2 gas with acid. You already know na, in our lower classes we have done, whenever a metal react with an acid, hydrogen gas is released. So whether the element will evolve H2 gas or not, we can easily find out with the help of the E0 values. For example, or I must tell you, the element having negative E0 value. E0 is what here? Reduction potential of electrode. Element having negative E0 value will evolve H2 gas, and the element having element having positive E naught value will not evolve H2 gas from acid. I'm talking about acid. From acid it will not evolve. Okay. We have seen, I have already told you the reactivity series, the Kedarnath ka Mali. See here, I have told you this. Now the potassium, sodium, calcium, magnesium, aluminium, zinc, iron, lead, they all lie above hydrogen. They all lie above hydrogen in the reactivity series. So they can easily displace hydrogen from the acid. And you can see copper, silver, they all lie below hydrogen. So they cannot displace hydrogen from the acid. Like your zinc having electrode potential Zn2 plus, reduction potential is minus 0.76 volt. Your copper is having Cu2 plus 2, Cu is plus 0.34 volt. So which will evolve the hydrogen gas? Yes, zinc can evolve. Copper cannot. You have seen this from this reactivity series. Yeah. Take a look here. You have seen copper lie below hydrogen, so it cannot displace. Yeah. Now to summarize all this, what we have told you in this class is, I'm giving you a simple question which will complete all the topics I have done with you. And you have to answer this. Okay. The question is, a cell is set up by dipping a copper rod in 1 molar CuSO4 solution and a nickel rod in 1 molar NiSO4 solution. The standard reduction potentials of copper and nickel are given. E naught Cu2 plus 2 Cu is what? 0.34 volt, and E naught Ni plus or Ni2 plus 2 Ni is given what? Negative minus 0.25 volt. Okay, so it is negative. Okay, now what you have to answer? You have to answer first which electrode will work as anode and which work as cathode. First you have to answer this. Okay. Secondly, you have to answer what is the cell reaction. I have already told you all these topics. What is the cell reaction? The third, you have to answer how the cell is represented, and the fourth is calculate the EMF of cell. So do. I'm giving you 5 minutes for doing that. Okay. Now let us discuss what is the solution for this question. Solution is, now a cell is set up by dipping a copper rod and a nickel rod in 1 molar solution of copper sulfate and a nickel sulfate respectively. The E naught potentials or the electrode potentials are given to you. With the help of these electrode potential, we can easily find out which electrode will work as anode and which electrode will work as cathode. Now, you know, the electrode with the negative electrode potential is the most reactive electrode, and it will work as anode. So what is the anode here? So the first part, nickel rod will work as anode here. Okay, so the negative is the most reactive and the The most reactive or the most negative is the better reducing agent, and the oxidation occur where? Oxidation occur on the negative electrode only. So nickel rod will work as anode and your copper rod will work as cathode. As simple as that. Yes. Now the second part, what is the cell reaction? Before writing the overall reaction, we must write the half cell reactions. Now what is anode and what is cathode here? You already know nickel is your anode. So what will happen to the nickel? Nickel solid will go into the solution as nickel 2 plus ion aqueous plus 2 electrons. So this is the oxidation half cell reaction. So this is what? This is the oxidation half cell reaction. And your this now next copper 2 plus aqueous. This copper is your cathode here, huh? 2 electron it will gain and it will form copper solid. And this is your reduction half cell reaction. Now what is the overall reaction? For overall reaction, you will what? You will add both the equations. Now if you, when you add these both equations, you will get what? You will get nickel, I'm adding na? Yes, you can look here. Yes, yes. Nickel solid plus copper 2 plus aqueous. These electrons cancel out each other and give rise to nickel 2 plus aqueous plus copper solid. Okay. Now what is the third part? Third part of the question. Third part is how the cell is represented. You all already know ABC rule. Anode, bridge, cathode. So what is anode here? Nickel is your anode. So nickel solid will convert into nickel 2 plus aqueous, and the bridge will give you this Cu 2 plus aqueous from Cu solid. So this is anode. What is happening at anode and what is happening at cathode? This is separated by the two parallel lines that represent a salt bridge. Now what is the fourth part of this question? Fourth part is the calculate the EMF of the cell. We have to calculate the E0 cell value. Now what is the E0 cell formula? Yes, it is E0 cathode minus E0 anode. Now what is cathode here? You already know copper is cathode here, and what is the E0 value for cathode? It is given to you 0.34. and what is the E0 value for nickel? Nickel, it is given to you as minus negative of 0.25 volt. Okay, now when you solve this, you will get a positive answer plus 0.59 volt. So this is the question. Another question I am discussing with you. A cell is set up between copper and silver electrodes as follows. So a cell representation is given to you: copper solid, copper 2 plus aqueous, bridge Ag plus aqueous, Ag solid. Okay. Now what if two half cell work under standard conditions? Calculate the EMF of the cell. Calculate the EMF of the cell, and you are given in bracket E0 values. E0, these all are your NCERT question I am discussing you. Okay, so E0 Cu2 plus 2Cu is 0.34 volt, and E0 Ag plus 2 Ag is 0.80 volt. Okay, now you have to calculate the EMF of the cell. And I am giving you 5 minutes to solve this question. Okay, let me discuss the answer with you. Yes, so what could be the possible solution for this? The possible solution for this, okay, E0 cell is what? E0 cell is E0 cathode, yes, minus E0 anode. Now what is cathode here? Your silver is your cathode. By the cell representation you can easily see. So 0.80 volt minus 0.34 volt will give you the value of plus 0.46 volt. So this is your answer. Okay. Now let me discuss with you the another question. That question says calculate the standard reduction potential. Calculate the standard reduction potential of CD2 plus CD 1 molar electrode. Instead of aqueous you can write 1 molar. Why we are writing 1 molar? You know the conditions are standard. Instead of, and 1 molar means it is in solution only. Okay, so calculate what we have to calculate the standard reduction potential of this cadmium electrode for the cell. Now cell is given zinc solid to zinc 2 plus 1 molar bridge CD2 plus 1 molar to CD solid. Okay, and your E0 cell is given to you 0.36 volt, and your E0 standard reduction potential for zinc is given to you minus 0.76 volt. Okay, let us solve this question. Now what could be the solution for this answer, this question, sorry? You know, E0 cell is equal to E0 cathode minus E0 anode. Now what is the cathode here? From the cell representation you can see cadmium electrode is your cathode, and E0 CD2 plus 2 CD you have to calculate. For anode it is given negative of 0.76 volt, and E0 cell is given to you 0.36 volt. When you solve this you will get CD2 plus 2 CD minus 0.40. So this is your answer. Okay, so far we have discussed your okay, see you then.